Hello students, today we are going to see about the integrator, the input-output waveforms of integrator, the function of integrator and the frequency response of integrator. So first we have to know what is an integrator circuit. So this circuit which integrates the given input signal with respect to time. Also, it allows only the low frequency signal and it attenuates the high frequency signal. So, it is essentially called as a low pass filter. Let us see the circuit diagram of an integrator circuit. Using operational amplifier, we are constructing the circuit for integration. So, we have two input terminals in operational amplifier IC741. This is inverting input terminal and non-inverting input terminal. To the inverting input terminal, connect the resistor and a capacitor is connected from the output terminal of the circuit to the input terminal, that is the inverting terminal. So, this capacitor is the feedback capacitor represented as CF, and this positive terminal, it is grounded. So, here the signal Vi is given through the resistor or to the inverting terminal of IC741, and this is the integrator circuit using IC741. So, before going to analyze the integrator, we have to recollect one information, that is the virtual ground concept. So, these two nodes should have the equal voltage in order to consider this Vd equal to 0. So, this node and this node must have equal voltage. So, here this positive terminal is grounded, and so the voltage at the negative terminal is 0 volt. The voltage at the negative terminal is 0 volt. So, the current drawn by the inverting terminal and non-inverting terminal both are 0. So, this is said to be IB minus and IB plus. IB minus is for inverting terminal and IB plus is for non-inverting terminal. So, both the currents are equal to 0. Right. And now consider this current, the current flowing through the resistor R as II and the current flowing through this capacitor as IC. And we have to have a relationship between the IC current and the output current IO. So, output terminal is this terminal. So, if you want to calculate the output current, this is the negative of the capacitor current, because the capacitor current is flowing from this 0 volt to this V0. And when we are going to calculate the output current IO, it is of opposite direction. So, IO is minus IC. So, this we have to remember. And now, consider this node as N. This node as N. To calculate the output voltage, we have to apply KCL at this node. Apply Kirchhoff's current law at node N. So, here we know that the Kirchhoff's current law states that the sum of the currents flowing towards the node is equal to the sum of current flowing away from the node. Here the current flowing towards the node is II and the current flowing away from the node is IC and IB minus. So, we know that this IB minus is equal to 0 since the input resistance of IC741 is infinite ideally. It is very high, so we consider the input current drawn by the input terminals as 0. So, consider this IB minus as 0 and the equation will become IC is equal to II. The input current is equal to the current flowing through the capacitance. Now, the current has to be written in terms of voltage and resistance and reactance and current voltage. So, here the II will be written as VI by R, and this IC will be CF d VC divided by dt. So, this is the voltage across the capacitor, and so if you want to calculate the output voltage, we have to write this capacitor voltage in terms of output voltage. So, this voltage will be actually equal to the output voltage. The capacitor voltage will be equal to the output voltage, but in the reverse direction. So, I am writing this as VI is equal to CF dV out VO divided by dt. And so, this II is equal to IC can be rewritten as II is equal to minus IO, that is the capacitor current and the output current has 180-degree phase shift. So, now minus has been included. So, for this if we write the equation, we will be getting CF into dV0 by dt. So, here we will keep this dV0 by dt in the left hand side. So, we will be getting minus VI or CF. So, here this dV0 by dt must be integrated in order to obtain the output voltage. So, on both the sides we have to integrate. This minus 1 by R CF is a constant value, only this VI will be integrated. Now, this integration and differentiation will get cancelled out, and V0 will be equal to minus 1 by R CF integral of VI dt. So, this is the output equation for the integrator circuit if the voltage across the capacitor initially is 0. If there is some voltage, we have to include as, if there is a voltage at the capacitor, we have to include VO at time is equal to 0. Next, we will be seeing about the frequency response of an integrator. So, for the frequency response, in x-axis we have to take the frequency in range, in y-axis gain in dB. So, this is frequency, this is gain in dB, decibels, this is in range. So, for this circuit, the frequency response will be like this. Okay. So, the curve touches this 0 dB line at say FO. So, here we have to have a relationship between the frequency and the gain. We know that from this equation, we know that the gain V0 by Vi will be equal to, so this is in inverting amplifier configuration. Instead of RF we have CF. For the inverting amplifier we know that the gain is minus RF by Ri. Here we can have, instead of minus RF, we can have this XC by Ri. Okay. So, the gain in magnitude, the absolute value if you calculate, the minus will go off, we will have only this XC Ri. This Xc can be rewritten as 1 by 2 pi Fc F into Ri. So, in the circuit we have taken this R as Ri as simply R. So I am putting this R, the same R in the equation. So this is the relationship between the gain, the magnitude of the gain and the frequency. Okay. So here it says that if the frequency is increased, the gain will be decreasing. So inversely proportional, the gain and the frequency are inversely proportional. So from this frequency response, we can also see that for lower range of frequency, the gain is maximum, and for higher range, the gain is reducing. And at one point, say it is FO, the gain touches this 0 dB line. So here the gain at 0 dB, frequency will be F0. So 0 dB in magnitude, it will be 1. So for 0 dB, if you calculate it in magnitude, it will be 1. So this is equated to 1 by 2 pi F CF R. So at F is equal to F0, we will be getting, so this F can be taken to the left hand side. So it will be 1 by 2 pi CF R. So this is the frequency where the curve touches the gain at 0 dB. Now we will discuss about the limitations of the normal integrator. So we have seen the normal integrator gain as minus Xc by R. Gain is equal to minus Xc by R. If you replace this Xc as 1 by 2 pi F into Cf, then the equation will become like this. So from this we can come to know that the gain is inversely proportional to the frequency, and the frequency response of the normal integrator, the blue curve. So for frequency 0, the gain is maximum, and if the frequency is increasing, the gain is reducing. So these are inversely proportional. So the curve is like this. So what is the limitation in the normal integrator is, when the frequency is low, the gain is high. So when the gain is high, it is directly proportional to Xc. The capacitive reactance will be very, very high. And in the circuit, so without this RF, the normal integrator circuit is this. So in the circuit, this capacitive reactance will become very high. So we will consider this as an open circuit. So there is no RF there in the normal integrator. So what will happen? The IC741 operation amplifier will work in an open loop configuration, and so the gain saturates at the value of either plus or minus V saturation. So gain saturates at plus or minus V saturation. So that will be the value here. So this is the where there is no integration happens. So that is why we are including this RF in the practical integrator circuit. So in parallel with the CF. So when you include this RF in parallel with CF, the gain will become the parallel combination of the capacitive reactance and the resistance divided by Ra. So instead of this Xc by R, we are going to have the parallel combination of the resistance and the capacitance, the capacitive reactance divided by R. So from this, if you do this calculation, you will be having the frequency, one particular frequency called Fa, which will be equal to 1 by 2 pi 1 by 2 pi Cf into Rf. So this Fa will be decided by these two components, Cf and Rf, and in the normal integrator we have calculated the frequency where the gain touches 0 dB line as 1 by 2 pi R into Cf. So this R is this R, the input resistor R, and the Cf. So these are the two frequency components we have to design for the integrator. And when you look at the frequency response curve for the practical integrator, so here the value, instead of saturated value, we will be getting this minus Rf by R, because this, if the capacitance is not there, when the capacitive reactance value is very high or it is open circuited, then you will be having only this Rf instead of this Xc parallel with Rf. So you will be having the gain as minus R of by R instead of the saturated value. So this will have some gain instead of the saturated gain. So you have the response curve like this, the flat response, and at one particular frequency the gain will be reduced here. So this is the frequency response of the low pass filter also. So this integrator will work like a low pass filter also. So this FA, this is decided by, as I said, it is 1 by 2 by CFRF. So then what is the range where the 100% integration is the range of 10 times of FA, that is 10 times of FA to FO. So that FA and FO we have already calculated. So from here 10 times of FA. So this is the range of the input signals frequency for which the integration will become 100% result. So before FA 0% integration, after FA to 10 times of FA it is 50% integration. After this only you will have 100% accurate integration will be there. And next we will be seeing about the input-output waveforms of the integrator. So as I said, it is essentially a low pass filter. It gives you the output for a lower frequency input. So this is the DC signal, a constant input. For this constant input, the output will be a ramp. If the amplitude of the constant input, if you take it as A, then the output will be A of T, A into T. So this is the ramp signal, and this is a decreasing ramp because the signal is given to the inverting input terminal of the operational amplifier. So, and if you give the input as square waveform, the output will be for the constant amplitude of the square waveform. The output will have a decreasing ramp. And this is the low frequency signal in the input. This is DC or low frequency signal in the input, and this part is high frequency signal in the input. So for this there is no change. So this is the maximum value. It is remains in the same state. So once the input signal varies from this time to this time, that is once the input signal has low frequency, then the output will have a positive ramp. So only the low frequency signal, the output will change from negative ramp to positive ramp for the positive half and the negative half. During the high frequency component, there is no output here. It is just a point. And you know that when you give a sine waveform, it will the integration result will be a cos, but you are giving the input to the non-inverting terminal, so the output will minus cos normally. So inverting terminal, if you give the input signal, then you will have a plus cos. So like this. So I hope you would have understand the integrated concept. Thank you.